So our last presentation for this session is Jon Rogers. Jon is the CEO of Locus Bioenergy. Jon is originally from UK. He has done his bachelor's from University of Liverpool and his MBA from University of Durham. Jon is an industry veteran with 30 plus years of experience at a very high level. He used to be the technical director for British Petroleum, executive vice president for Clarion Technology, as well as managing director for Sasol, and so on. So today, Jon will be talking about biosurfactant and driving new value in saltwater disposal wells. So let's welcome Jon.
Good afternoon, ladies and gentlemen, and thank you very much for this invitation to come and talk today. When I first started looking at what I was going to talk about today, I realized that I've been now in the oil and gas business for over 35 years, worked in most basins around the world, and have a lot of experience where we used to re-inject produced water brines. So why can we have systems around the world where we're injecting saturated brines as wastewater into similar sort of sandstone formations, and yet those wells typically can last 8 to 10 years without the need for remediation or acid, but in the Permian, we can be acidizing or remediating a Permian saltwater disposal well 3 or 4 times a year. And a lot of what I'm going to touch on is exactly what Curtis has spoke about, this unique cocktail that we have that we're actually injecting and the sheer volume that we've got to get rid of. So what I'm going to talk about is a solution that we've come up with, which is, first of all, effective, but secondly, cost effective. As you'll see, we're going to have 19 billion barrels a year to dispose of in this water. You couldn't have a treatment costing $1 a barrel. So it's got to be cost effective, otherwise we'll carry on what we're doing now, which is basically no treatment. Great. So I mentioned about the sheer volume, and one of the things that was quite interesting last week, if you read it, was that BP updated its predictions for the energy transition we're supposed to go through between now and 2050. And of course, what has thrown the whole thing out is the Russian-Ukraine war and the fact that now we've got these, what they call this trilemma of security of supply, affordability, and sustainability. So what you're looking at here is, on the left-hand side, this is what BP thought the mix would be of different oil productions as we went through this energy transition. Now, for this decade, they always assumed that we would still keep US tight oil production around about that 10, 11 million barrels, maybe going up to 12, but then once we got to 2030 onwards, basically shale would start to come down. Now what they've realized is what they're calling the new momentum, which is basically the fact of life, is we're actually going to have to increase tight oil by about 33% this decade. Now, what does that mean? The so what for produced water is, if you look at what we produced last year in the Permian, as I mentioned, it's 7 billion barrels, or about 19 million barrels per day. Even if we were able to take all the frac water we need and use produced water, that's still only going to be about 2.1 billion barrels a year. So we've still got to find a way, in the best case scenario, of disposing of 13 million barrels a day. Now, with this increase in the tight oil, that number is likely to go up by another 33%, because they think that US tight shale could peak at about 16 million barrels a day as we get towards the end of the decade. Then we have other issues which we're all aware of here, and it's not just the fact that we lack capacity, but even the capacity that we've got is not performing as per design. And the bottom line is we're hitting the maximum allowable pressure way before we hit the allowable injection volumes. So much so that obviously everybody's aware of the seismicity issues that we've had. There's been 102 events of over magnitude 3.5 since 2014. And then just last November, if you remember, the Culberson County actually had a magnitude 5.2. There were 78 disposal wells in that area. Since then, the injection capacity has gone down by 70%. If they have another quake in that same area, that SWD production will be shut in for at least 2 years. So we've got a massive problem here. As I mentioned, this is the reason that we're struggling now, and even in some of these seismic response areas where we can't inject, we're having to take that water, transport it to other parts of the world, other parts of the region rather, and inject it there. So if we're ever concerned about carbon footprint and the cost of trucking it, that's a massive cost. So what's the solution? Well, to look at the solution, we've got to look at what is the cause. Now, produced water is contaminated. I think we all know that. But what's amazing is if you look at the iron content that Curtis mentioned, a typical connate water in a normal field around the world is probably about 5 ppm, 5 parts per million. And a lot of that is actually from system corrosion. Shale and mud basins actually contain a lot of indigenous iron. If you look at the Midland Formation, the Permian, it's about 55 parts per million. You go up to the Bakken, it's 133. There's a lot more iron there. Now, if you combine that with the fact that the solids content in produced water is high, we have about 2,000 ppm of particles less than 30 microns. And that comes from corrosion products, it's crushed proppant sand. So what we've basically got is a paste. Now, the glue for that paste is something that Curtis mentioned. Not only have we got iron in the form of small iron sulfide particles, which in themselves should, from the size exclusion, pass into the formation, but it's, as Curtis said, it's the colloidal iron, which is basically what they call iron oxyhydroxide, which is a charged particle which is acting as the paste on these particles. And what we're getting very close to the injection face in these injection wells is basically a very low permeability filter cake that blocks up the injection route for the water. So we're agreed on that. What we're also agreed on is if you're going to do any water treatment at the moment, it's expensive. If you're going to do flocculation, if you're going to do dissolved air flotation, if you're going to do filtration, that puts a significant cost on the treatment costs for the water. And again, remember, we're talking billions of barrels a year. So what happens is most of the water that goes for disposal has little, if any, treatment. The next slide I'll show that in theory, to try and avoid a lot of the issues that were mentioned before, we should stop that iron from oxidizing, but we don't, because gas blanketing is expensive. So what do we need? We need a cheap but effective treatment that will stop this problem of this very dense, low permeability filter cake, and instead will transform these solids into something that forms a very light, highly permeable filter cake, which allows more of that water to pass into the reservoir and be safely disposed without having a high back pressure come up. So what I just mentioned is really figuratively shown here. So we can actually reproduce the formation of this low permeability filter cake that we get. Again, this is the silica, it's solids, it's grease, it's wax, and it's also this colloidal matter. Think of it like spongy, wispy iron that's in the water. So the test that I'll show you, which a lot of companies, I think like OLA that Robert works for, use is basically to take a 0.45 micron filter in the field, take the actual field water before it's oxidized, before it's got contaminated, and actually push it through and see how much water you can get through that filter in a certain amount of time. And there's a correlation there between the filter plugging capability and therefore the reservoir plugging capability of your water, treated and untreated. So this is the test that we run. It's fairly basic, but what we're showing here is this is the Frac pond water as is. Then when it's oxidized, you see the colloidal matter, this combination of the sticky oxyhydroxides plus the silica that's come out, the small particles that have come out, the 30 micron and less, and grease. And what you end up with is that mass that will form that filter cake. It will settle, it will come out. That's the first thing that comes on the wall of your injection surface and stops the rest of the flow building up. So the cost-effective, and we're talking cents per barrel, that we've come up with is a combination ion treatment and dispersant using our product, which are biosurfactants. Now, biosurfactants, think of a normal surfactant we use as soap. Think of one of those on steroids. Think of one of pharmaceutical complexity. Very stable, but you only need a fraction of the concentration of what you need with a normal surfactant. So it's extremely cost effective. So we're talking ppm and cents per barrel rather than tens of cents per barrel. And what we're doing basically, it's not rocket science, is we're actually finding, because these products are great dispersants, they will keep apart the grease, the silica, the colloidal matter, and they'll keep it suspended for a period where you can actually inject it in. You're not going to get that buildup right near the reservoir face, and you can pass more water in. Let me show you that in practice. This is basically the test that we do in the lab. And you can see here all the contaminants that we've got on the left-hand side. That's exactly the same water that's now been treated with ppm levels of this dispersant that we've got. And what you see is the difference in the filter cake that you get. So in the sort of undispersed, you get a thick, dense, not very permeable filter cake, which takes a long time then for the water to go through. What you get with the biosurfactant, we call it flow boost, is we get a very dispersed cake, and that cake is very permeable. Even that cake will allow water to pass through it. So the field test that we do is this. What you're looking at on the left is untreated water, very similar to what is injected every day. On the right-hand side is water treated with parts per million. Now, what you'll see is that all of the water in the right-hand side has passed through that filter, because the filter, even though it's got the same amount of solids in, has formed a very permeable filter cake. It's finished in 20 seconds. What you're looking at here is it took almost 3 minutes for the water on the left-hand side to finally go through. So again, we're not eliminating the solids problem. What we're doing is we're forming a filter cake that when we get in the reservoir is permeable, allows more water in before the back pressure comes out. There's another benefit of biosurfactant. In addition to being a dispersant, one of the other treatments that we use it for is we actually use it as an emulsion breaker and a wax dispersant downhole. So it will actually change the wettability of the rock we're injecting into and increase the injectivity. One of the case histories we've got, which I'm going to show you, is we had a system. Let me just go through that. I'll go to that and then I'll come back. This is a system that we had where the injection pressure had gone up. They tried all types of surfactant, even backwashing, and could not get the pressure to come down. We just batch dosed in, basically slugged in 250 ppm of our product. Within 2 days, the injection pressure went down initially by 12% and then eventually by 20%. So this treatment can either be used as a batch or can be used continuously, depending on the severeness of the fouling. But this paste of the small particles, 30 microns, the colloidal ion, can also cause problems in emulsion pads. Most people will say that where we've got the skim tanks, there's oil there, but the oil is like a paste, you can't recover it. So one of the things that we're finding is we actually get a clean break. Because we're removing the solids from the oil, that oil can be removed and is saleable. So right through the system, there's benefits, but the biggest benefit is the lower back pressure, the extended intervals between acidization, and in some cases, the ability to just inject more below whatever the maximum allowable pressure is. Now, if you do have to acidize, great point again that Curtis made, I think we should go on tour together going forward, is a lot of the times that when you put an acid in, one of the reasons the acid is not so effective is it actually can't get to where you want it to go, to the carbonate, to wherever the particles are, the iron. So the ability to wash the oil off is what the biosurfactant does really well. And that's exactly the same attribute that separates the oil from the solids in the skim tank. What we do is we've actually got an experiment here where we had oil-coated solids. In this case, it was carbonate. A lot of people, when they're acidize, will put in a xylene spearhead to try and clear that oil off so the acid get to it. And what you're looking at here is we just did 1.5% acid because at 15% acid, the reaction was too quick on all three. 1.5% acid where we've baked on oil onto carbonate chips. The second one is a typical acidizing pill where you're going in first of all with xylene, then going in with acid. And then on the right-hand side is just 3% of our product. Now you can show, or you can see the efficacy of the penetration of the acid because of the, if you look on the right-hand side, you can actually see where we're actually dissolving the acid and forming the carbon dioxide layer on top. So again, washing the oil off the solids, allowing the acid you put in to do more useful work. You can see the difference in the 3 bottles, a significant difference. Again, at 3% of our water-based biosurfactant solution versus xylene. What you're looking at the top picture is taking those same bottles, turning on the side, and you can see that the acid alone was still oil wet. In the middle, we've had some removal of the oil. On the right-hand side, you can see we've separated the oil and water into 2 distinct layers. Again, think skim tank. What you can also see is the amount of solid matter left is a lot less because that acid is able to do more useful work. So this product was launched about 18 months ago. We are currently treating about 27 SWDs. We will be doing about 50 by the middle of the year. And we believe it's not a one-size-fits-all. We will adjust the formulation as need be. But what we've got now is a cost-effective alternative to either very high-cost filtration, separation, water treatment plants and doing nothing. We've been recognized by the Hart Energy Award as a winner of their Special Meritorious Award for Engineering, and we were World Oil and also S&P Global Energy. So we would love to talk to operators here about how we can help. But as I say, we have something that now can be done at cents per barrel and hopefully becomes a viable tool that we can use to help increase the disposal rates of produced water in the Permian Basin. Thank you very much.
Thank you so much, John. So question for John. Please introduce yourself first. Don't go anywhere, John.
Steve Appleyard with Conoco Phillips. I just wondered, spent triazine is quite an issue in disposal wells with the particulate dithiazine polymer. Have you tried this dispersant with that kind of foulant as well as the iron that you talked about?
Not specifically, Steve, but we do have, what we typically do is go to the field. We can actually mix in a suitable dispersant if the package we've got doesn't work. So I say we tweak the formulation for a different field, but to answer your question, no, not specifically with spent triazine or triazine solids.
You may have said it and I missed it, but does the reduction of pressure correlate directly with formations?
I think it's inferred there's a connection because obviously we're putting more stress on the injecting formations. Obviously, we're limiting back pressure, but there's assumption that the volumes and the pressures we're pumping at are contributing to seismicity. I don't think we'll ever get to the point where the pressure is so high that we're inducing seismicity, but there's obviously a correlation between the two.
Yes, question please. This is Joe D'Almeida with Oxy. I was thinking about your slide you had up there with the filter and with the biosurfactant that was added. I just want to be sure, am I clear in my understanding that the biosurfactant, the purpose of it is to allow the solids to carry forward into the formation and avoid that? Is it acting like a suspension agent, I guess? Could you clarify that a little bit, please?
Right.
And if, a related question, on the biosurfactants, are you sending when you were doing the dosing down hole, are you sending microbial community down there to generate the surfactant? Are you generating up top? And if you could expand on that, please.
Certainly. So there's nothing live that we put in. This is not sort of microbial EOR that was going years ago. We're actually making these products ex situ. We're making them in a fermentation plant in Cleveland. You use them and treat them like a normal surfactant. What they do is, at very low dosages, they have great dispersibility of both solids and oil and grease. So what we're doing is we're actually dispersing the solution so you don't get this cake that drops straight down to the bottom of the filter. But also what you end up is the filter cake you do get is a higher permeability. So that filter cake's got to come out somewhere, but if you can make it a filter cake where you can actually still pass fluids through, as opposed to this dense, low permeability filter cake that we get at the moment, that will improve the injectivity, and you'll get a lot more water through before you actually get the back pressure that means you have to do an intervention.
Hey, John, very good presentation. Thank you. Rick McCurdy with Select Energy Services. So years ago, along with mutual solvents, as you mentioned, like xylene, industry historically used like micellar acid additives to do that de-oiling for acids. And those products work very well. Predominantly, they were usually mostly a product called EGMBE, right? Which worked well, typically, but you had to be in about a 5 to 10% concentration in the acid. And it also had kind of a nasty environmental footprint. Could you kind of talk to your product's environmental footprint versus something like EGMB?
Yeah. So the biosurfactant itself is low toxicity, and it is also, in this particular case, it's a water-based microemulsion. So we put it in the acid at about 3%, but once it's done its job, once you float it out and you get the waste back to wherever you're going to treat it, it biodegrades down within 30 days. So its toxicity of the biosurfactant is about 10 times lower than a typical alkoxylate surfactant that you would use. So toxicity is not an issue.
All right, thanks a lot.
Thanks.
Hi, John. This is Ryan from SOMAM. I'm just wondering, will the use of the biosurfactant change the, let's say, the surface tension or the mobility of whatever water you are injecting to the underground aquifer? Such as previously, let's say the aquifer is a confined aquifer, but then the mobility of the water increased a lot, then the aquifer is no longer a confined aquifer. Have you investigated issues like this?
We haven't, for sure. In some of the applications we use the biosurfactant for, we're changing the surface wettability, we're changing the contact angle. So we haven't done core flood tests to do that, but I would say that certainly the biggest problem that we've got at the moment is the filter cake to overcome that, but certainly it's something we need to look into. Are we adversely affecting the transportation or the wettability of the reservoir?
Thank you.
Can I do one more? Yeah, Dan Shannon with Select Energy Services. What's the charge of the surfactant?
Neutral.
Neutral, thank you.
Joe D'Almeida with Oxy again. Yes, given what results you shared up here, and you did hit on the major topic of seismicity, and you're making the sound rather cost effective, right, cents per barrel. I wonder what has been the response so far from the midstream companies, whether it's NGL or Select Energy or Aris and all these others. And the other related question is, it would seem the Railroad Commission would be very interested in something like this as a solution, as they're concerned about revenues to the state being choked back. I wonder if you could share what's been going on from that business model standpoint.
For sure. So at the moment now, our model is to go to the market through service companies. So as I mentioned, we've got about 27 wells at the moment that we're working with partner companies on, going to go up to 50. Part of me being here today is for the awareness to get more companies involved. We do have relationships with Texas RRC. In fact, our product that we call STIM actually qualified for the Texas Railroad Commission severance tax credit about 2 or 3 years ago. So we know Wayne Christian, and they're very aware of new technology that's coming through. So for sure, this is part of what my job is, to get out, get awareness, get people testing, field trialing, build up the data set, and absolutely take it to more and more companies.
Real quick, Robert Mitchell, OLA, is temperature a driver for your products? Does the temperature help or hurt it? Do you put your product in the front of the system, therefore carrying more solids to the end of the system, or have you done it both, pre-gun barrel versus last settling tanks?
We worked across the board. Again, I think it was another maybe analogy I can give you. We actually have also used this product in a traditional water injection system. So sometimes we can mobilize too many solids, or we can disperse too many solids and do a cleanup. So it depends what you want to do. This is why we'll survey the system. Certainly want to be upstream of the skim tank typically to get that oil separation. But going back to water injection, we actually had a couple of injectors where we put the treatment in and actually saw that we were mobilizing some heavy organics because the assay of the producer actually changed. So we know from our oil treatments, we can mobilize and disperse solids so they actually come out of the system. So it very much depends on the system design and what the fouling is and where do you want we can mobilize solids, where do you want them to go?
Thank you, John. Let's give a big round of applause for all 3 of our speakers, okay?